Okay, this video will go over the graphs of the sine and cosine functions. Alright. And we're also going to go over sinusoidal curve fitting. It's pretty much when you transform a sine or cosine graph. Let's begin with restating some basic properties about the sine function. Remember, for the sine curve, the domain is the set of all real numbers. The range is contained in the interval from -1 to +1. And it says inclusive, which means it does include the endpoints -1 and +1 respectively. We already stated that's an odd function, that it has a period of 2 pi. We've noted that it crosses the x-intercept at these points. We know that whenever we had to graph 1 over the sine, which would be the cosecant. We notice because those are the values that make the cosecant undefined. And our absolute maximum is 1 and occurs at these points. And our absolute minimum is -1 and occurs at these points. And here's a graph in case you've forgotten. As you see, the sine's equal to 0 at these intervals of pi that we stated. It's equal to 1 at these intervals of pi that we stated before. And -1 here. Now let's see what happens if we do any sort of transformations. Alright, let's talk about how we can transform a graph.
Yeah.
Say we're doing something to the sine function, some number times sine of times w times x minus, let's say, the Greek letter phi plus the Greek letter beta. Now the amplitude is how much you stretch the graph. It's just equal to the absolute value of the number in front. The period of our transformed graph is equal to, remember, if it's sine or cosine, the period is normally 2 pi, so it'd be 2 pi over w. Because the number in front of x affects how often it crosses the x-axis. It affects the period, the rate at which it starts over. Now, something we call the phase shift, which controls how much it's shifted left or right. That's equal to, the phase shift would be x equals v over w. Pretty much, see, if we're subtracting, then whenever we solve for x, it'd be positive. Since our x is positive, that means we would shift to the right if it's subtracting. And if we're adding inside the parentheses, that means when we solve for the phase shift here, we'd end up getting a negative number if it was positive here. So, if it's positive inside the parentheses, then it would be a phase shift to the left. And if it's negative inside the parentheses, it'd be a phase shift to the right. Now we also have a vertical shift. And that's controlled by the Greek letter beta. Pretty much, if beta is positive, that means you shift the graph upward. If beta is minus, that means you shift the graph. If beta is negative, you shift the graph downward. Alright, so here's an example. You can do graph y equals 3 sine of x using transformations. Okay, the amplitude is equal to the absolute value of the number in front, which is 3. So that means it's stretched by a factor of 3. So instead of it being contained between 1 and -1, it would be contained between -3 and +3. So if you look at the graph of the normal sine function, it goes between -1 and +1. So that means these points where it's -1 would now be located up here at 3. So this point here would be down here now. That point would be up here. This point here would now be down here. This point here would be up here. It would still cross the x-axis at the same place. It still crosses the x-axis because we didn't do anything to the phase shift. It's not shifted to the left or right any. We didn't change the period. All we did was change how much it stretched by. And let me put up a nice neat picture of what the graph of this sinusoidal curve would look like. And this is what it'd look like. You notice it still crosses the x-axis at the same locations. Just that it goes from -3 to +3 because the amplitude is 3. Alright, here's another example. Graph y equals negative sine of 2x using transformations. Alright, let's go ahead and pull out the graph of the regular sine function so that we can use that as a reference. Alright, here's the graph of our regular sine function. Alright, we have the negative sign in front, so everything that's below the x-axis is now above the x-axis. Everything that's above the x-axis is below. We can start by applying that, and then this 2 in front of x. Remember, that affects the period. So remember, the period is 2 pi divided by the number in front, which means the period is now just pi. Which means this point here where it starts over is now located right here. This period here at pi over 2 is now located at, well, the one that's down here at pi over 2 is now located here at pi over 4. This point here at pi, that 0 is now located at pi over 2 because remember, it cuts the period in half. This period over here at 1. At +1. Since it's at 3 pi over 2, you cut it in half, so 3 pi over 2 times 1/2 means it's located now at 3 pi over 4. And then this point here would be at pi. So this is what it would look like. And this point here, that would be at now +1 at negative pi over 2. If you multiply that by 1/2, it would be at negative pi over 4. So if you see it's compressed into half the space, that's what changing the period does. Now let's go over the graph of the cosine function. Let's start by restating some facts about the cosine function. Alright, so we said the domain is the set of all real numbers. Like the sine, the cosine is contained between the numbers -1 and 1 in the y direction, so the range is from -1 to +1 inclusive. We said that cosine was even, and that's periodic with a period of 2 pi. And if you remember from looking at the graph, these are where it crosses the x-axis. And the absolute maximum is +1, and the absolute minimum is -1. And it occurs at these points, pi, 3 pi, 5 pi, etc. And here's a picture of the graph in case you've forgotten what it looks like. Here's the graph. Here where it crosses the x-axis, like what we stated on the previous slide. Here are some of the intervals where it's equal to +1, at 0, 2 pi, -2 pi. And if it kept going, it'd be at like 4 pi, 6 pi, 8 pi, likewise in the negative direction. And it's equal to -1 at intervals of pi with odd coefficients. Now, let's practice doing some transformations with the cosine function. Alright, let's go over how to graph this using transformations. Let me start off by putting up the graph of the cosine function up here to use as a reference. Alright, this 2 in front means the amplitude would be 2, so you can, every place where it's 1, you'd bump it up to 2. Every place where it's -1, you'd bump it down to -2. So like for This point negative pi, negative 1, it'd be at negative 2. At this point here where it's negative 1 at pi, you'd bump it down to negative 2 again. This point here where it's positive 1, you'd bump it up to positive 2. Now this 3 in front of the x, that changes the period. So it'd be 2 pi over the number in front. So this period is now 2 pi over 3. So the way you do it is you start here where it's 0 and this place where it's pi. Since you cut the period by a third, instead of pi, it'd be at pi over 3, which would be at about right here, I think. Actually, you start off by this one. Pi over 2. Since it crosses 0 at pi over 2, it would now cross at pi over 6. At pi, since it's negative 2 at pi, now it'd be negative 2 at pi over 3. Since it's now 0 at 3 pi over, since it's 0 at 3 pi over 2 originally, if you cut it by a third, 3 pi over 2 times 1/3 would be 3 pi over 6 or pi over 2. Since it's now 2, or since it's now 1 at 2 pi, multiply it by a third is now 1 at 2 pi over 3. Or it'd actually be 2 now. So if we draw our new graph, it'll look something like that, except hopefully your graph looks a lot better than mine. Let me pull up a picture, a neat picture of what it would look like. Like what we said here, or on the previous slide, instead of crossing the x-axis at pi over 2, we multiply by 1/3, so it crossed at pi over 6 like what we said. And instead of it being negative 2 at pi over 3, or instead of it being negative 2 at pi, it's now negative 2 at pi over 3. And instead of it being positive 2 at 2 pi, it was positive 2 at 2 pi over 3, like what we said. So here's an example graph, cosine of x minus pi over 2. Since we're doing with cosine, let's put the graph with the cosine up here as a reference. Alright, since we're subtracting pi over 2 from x, that means the phase shift would be pi over 2 to the right. So that means each of these points, I'd recommend finding what we call the critical points, the points where it's 1, -1, or 0, and just shifting all these critical points pi over 2 units to the right. So this point where it's -1 at pi, it'd now be at pi over 2. This point here where it's 0 at negative pi over 2, it'd now be 0 at 0. This point where it's positive 1 at 0, it'd now be positive 1 at pi over 2. This point where it's 0 at pi over 2, it'd now be 0 at pi. This point where it's -1 at pi, it'd be -1 at 3 pi over 2. And this point at 3 pi over 2 where it's 0, it'd now be 0 at 2 pi. And this point here where it's equal to 1 at 2 pi, it'd now be equal to 1 at 5 pi over 2. So if you connect these dots, these points, if you notice, this looks like the sine graph. So if you notice, the cosine of x minus pi over 2 is actually equal to the sine of x. That's why we can call this, like whenever we shift a cosine graph around, that's why we can call that a sinusoidal function as well instead of a cosinusoidal. Because a cosine is just a phase shift of the sine function. Conversely, or likewise, if you were to take this new sine function and shift it back to the left pi over 2, that would be equal to the cosine function. Shift the cosine function to the right to get the sine function, so we have to shift the sine function back left to get the cosine. Now here's an example. Determine the amplitude and period of y equals 3 sine of 4x. Now the amplitude, that's equal to the absolute value of the number in front, so it'd just be 3. And the period of sine is normally 2 pi, but it has a number of 4 in front, so the period is now pi over 2. Alright, so now we're going to learn how to graph a function using just the key points without using the original sine function as a reference. Alright, we know the amplitude is 3. And the period is 2 pi over 4, which is pi over 2. Which means we cut the period by 1/4. So, each place where it'd be equal to 1, or in this case 3 since the amplitude is 3, we would multiply that x value by 1/4. So I believe it's still equal to 0 at intervals of at 0 and at right. Well, normally the sine graph would be equal to 0 would be at the point 0, 0, at pi 0, and at 2 pi 0, etc. But since we multiply it by 1/4, the x-intercept would now be at 0, 0, pi over 4, 0. Instead of pi, it'd be at pi over 4. At 2 pi over 4, or at pi over 2. Why do I keep doing that? See, I believe this is where it is. See, and it'd be also at like 3 pi, 0, etc. So instead of at 3 pi, it'd be at 3 pi over 4, etc. And that'd be equal to 1 at intervals of like pi over 2, 5 pi over 2. Except that now, instead of it being located at positive 1, it'd be at positive 3. Because the amplitude is 3, so it stretches it by a factor of 3. Pi over 2. I believe that would also be located at 9 pi over 2. Which means they would now be located at, if you multiply everything by 1/4, it'd be at pi over 8. Because pi over 2 multiplied by 1/4 would be pi over 8. At 5 pi over 2 multiplied by 1/4, it'd be at 5 pi over 8. At 9 pi over 2 multiplied by 1/4, it'd be at 9 pi over 8. 3. Keep going on and on. Now I believe it's located at negative 1 at intervals of, I believe it'd be 3 pi over 2, and it'd technically be at negative 3 now, because the amplitude is 3. 3 pi over 2, 7 pi over 2, 11 pi over 2, etc. So this means it would now be located, if you multiply everything by 1/4, it'd be at 3 pi over 8. And instead of 7 pi over 2, multiply it by 1/4, it's 7 pi over 8. Instead of 11 pi over 2, it'd be 11 pi over 8. And you can keep going, but if you plot these key points now that we've identified by the 3 arrows, you should get the following graph. Alright, here's a picture of the graph we did with all the points labeled that we came up with, and a few extras. Alright, next example we're going to do is graph this function using the key points, meaning where it's equal to 1, -1, or 0. So, I'd recommend first thing if you can rewrite it. We know sine's an odd function, so you could move the negative to the outside since it's odd. So it's negative 2 sine of pi over 2 x. So now the amplitude would be absolute value of negative 2, which is just 2. And the period would be 2 pi divided by pi over 2. So it'd be, remember you could do keep flip change 2 pi times 2 over pi. The pi's cancel out, so you're left with a period of just 4. Alright, so we know our sine function would normally be 0 at the points, or at the origin, at pi, at 2 pi, etc. But since we have to multiply it by 2 over pi, that means that it would now be still be equal to 0 at the origin. That instead of it being at pi, you have to multiply it by 2 over pi. So it'd be at the point 2, 0. And instead of it being at 2 pi, it'd be at the point 4, 0. Now the sine function would normally be equal to 1, or in this case 2, since the amplitude is 2, at pi over 2. Well, since it's negative, it'd be at negative 2, because remember, you have to flip it across the x-axis. And it would normally be at 1, or in this case, negative 2, at 5 pi over 2, and at 9 pi over 2, etc. But since we have to multiply the points by 2 over pi, it'd be at 1, negative 2, at 5, negative 2, and at 9, negative 2. It would normally be equal at negative 1, or in this case, positive 2. Since it's negative in front, you'd have to flip it across the x-axis. So it would normally be at negative 1, or in this case, positive 2 at, I believe, 3 pi over 2, 7 pi over 2, at 11 pi over 2, etc. So now, in order to count for the period, you have to multiply it by 2 over pi. So now it'd be at the point 3, 2. At the point, instead of 7 pi over 2, multiply by 2 over pi, and you get 7 over 2. And at 11, 2. So now, you have your point, your critical points here, here, and here. You can pause, and now you can draw your graph, and it should come out looking like. Alright, here's the graph with the points we labeled 0, 0, 2, 0, and 4, 0. So here's another example. It says find the equation for the graph in figure 60. We can start by figuring out the amplitude. The amplitude goes from 3 to negative 3. So, you know the amplitude would just be 3. And the period, since this looks like either the sine or cosine function, period is 1, so the period you would do by taking the formula 2 pi over w. I think your book's actually trying to use the Greek letter, lowercase omega, but it looks like a w. 2 pi over omega equals 1. So if you solve for omega, that would be omega equals 2 pi over 1, which means the number in front of x would just be 2 pi. So the equation of your graph would be 3 times, if you remember, sine actually starts on the x-axis, starts at the origin and goes like this, whereas cosine starts along the y-axis and goes like this. So it actually looks more like the cosine function, so it'd be 3 cosine of 2 pi x. So now here's another example for you. Find the equation shown in this graph. Now, you notice this looks more like the sine graph than the cosine graph, so you know it's going to be sine of something. You have the period labeled for you here, so the period is 4. So it'd be 4 equals 2 pi over omega, which means omega is equal to 2 pi over 4, which would be pi over 2. Now it looks almost like the sine function, except the sine looks like sine normally goes in this way. It's like where it's above the y-axis, it's normally below. Where it's normally below the x-axis, right here it'd normally be above, because you see it normally goes like this, but since it's going downward, you know it'd be a negative number in front. And the amplitude, it goes from -2 to +2, so the amplitude is 2, so it's equal to -2 because it's flipped, and the amplitude is 2 times the sine of pi over 2 x. Alright, here's another example of a sinusoidal curve. It says find the amplitude, period, and phase shift of y equals 3 sine of 2x minus pi, and graph the function. Alright, let's first find the amplitude, period, and phase shift. The amplitude is just 3 because that's the number in front. The period is 2 pi divided by the number in front of x, so it's just pi. And the phase shift alright, so phase shift, you can start by finding the phase shift by factoring out the number in front of x. So you have x minus pi over 2. If our original statement is 2x minus pi and you factor out the 2, you're left with x minus pi over 2. So if you take that, so x minus pi over 2 is 0. If you solve it for x, your phase shift is positive pi over 2. So this phase, since x equals pi over 2, that means the entire graph is shifted pi over 2 to the right. So remember, whenever you're graphing these, I'd first recommend applying the period, or the amplitude and the period first, because that controls how much it's stretched or compressed both horizontally and vertically. And then control how much it's then change how much it's affected, left, right, or up or down. So we'll actually graph it on the following slide, and I'll put up the graph of the original sine function as a reference. Alright, we're going to start with our original function, the graph of sine of x. Our amplitude was 3. Our period was, I believe it was pi. And our phase shift was positive pi over 2. So it's pi over 2 to the right. So let me show you what happens with these graphs first. So instead of it being at 1 and -1, those points would be at 3 and -3. So drop those points down. These points would still be at 0. And then the points that are at positive 1 would be at positive 3. Now the period is pi because we cut everything in half. So this point, so you multiply all the x points by 1/2 since we cut the period in half. So this point's at the point 0, 0. So it would stay at 0, 0. This point at negative pi over 2, multiply it by 1/2, and it would now be at negative pi over 4. This point here that's at positive pi over 2, multiply it by 1/2, it'd now be at positive pi over 4. This point here that's at pi, it'd now be at pi over 2. This point here that's at 3 pi over 2, multiply it by 1/2, it'd now be at 3 pi over 4. This point here, that's at 2 pi multiplied by 1/2, and it'd be at pi. This point here, that's at 5 pi over 2, it'd now be at 5 pi over 4. So if we were to draw our graph, this is what it looks like so far, with the period and the amplitude applied. But we still need to shift it over pi over 2 to the right. So this point here that's at 0 is at pi over 2. This point here that's at pi over 4 is now at 3 pi over 4. This point here that's at 3 pi over 4 is now at 5 pi over 4. This period this point that's at pi is now at 3 pi over 2, and this point here that's at 3 pi over 2 is now at 2 pi. So your new graph would actually look something like this. It'd look like the purple graph. And let me pull up a picture of what it should look like, assuming your instructor could actually draw. Alright, so here's what the graph would look like, assuming I could actually draw an accurate graph. So you notice the period got switched to pi. So here's another example. Graph y equals 2 times cosine of 4x plus 3 pi plus 1. Also find the period, amplitude, and phase shift. Alright, the amplitude is just 2 because it's the number in front of the cosine. The period would be 2 pi divided by the number in front of x, so the period is actually cut down by 1/4. And then the phase shift, you factor out the number in front of x, so it'd be 4 times, open parentheses, x plus 3 pi over 4. So you take this x plus 3 pi over 4, you can set it equal to 0, which means x is equal to negative 3 pi over 4. That means you shift it, the entire graph 3 pi over 4 to the left. And also see this plus 1 on the end? That means you also have a vertical, at the very end, you'll shift the entire graph up 1 unit. So here's our original graph of the cosine function. And we said our amplitude was 2, so each point where it's at 1 is now at 2. Or negative 2, respectively. Now, we said that the period was equal to, the period was pi over 2, which means the entire period was cut down by 1/4. So multiply all the x coordinates by 1/4. So this point 0, 2 would stay the same. This point pi over 2, 0 would now be at pi over 8, 0. This point here at pi, since it's cut down by 1/4, you multiply by pi over 4 and it'd be at pi over 4. This point here at 3 pi over 2 would now be at 3 pi over 8. Would be about right here, halfway between pi over 4 and pi over 2. This point here at 2 pi, multiply by pi over 4 and it'd now be at pi over 2. This point here at negative pi over 2, or negative pi comma, negative 2. Multiply that by 1/4, it'd be at negative pi over 4. So there's our graph so far. We shifted it 3 pi over 4 to the right. So this entire graph here, I'm going to start by doing it by this endpoint here, pi over 2, if we shift it 3 pi over 4 to the right. Actually, it'd be shifted to the left, rather, because I just remembered it's 3 pi over 4 to the left, so take the left endpoint. You could start by this point here. This negative pi over 4, if we shift it 3 pi over 4, it would now be at, I believe it's at pi. This point here where it's at 0, pi over 8, it'd be at 7 pi over 8. This point here, that's at 0, it'd be at 3 pi over 4. This point here, at positive pi over 4. If you shifted 3 pi over 4 to the left, it'd be pi over 4 minus 3 pi over 4. So that'd be negative pi over 2, because you know negative 2 pi over 4. This point here, or that'd be at pi over 8, I believe. This point here at pi over 4, this point here at pi over 4 negative 2 would be at pi over 2. Alright. So this point here at pi over 4 negative 2, that's the one that should be at pi over 2. This point here, I believe that is actually at pi over 8. So pi over 8 minus 3 pi over 2, because we're shifting it to the left. That would be at negative 6 pi over 8 minus 6 pi over 8 would be negative 5 pi over 8. So it'd be right here. So this point here at 3 pi over, I believe that's 3 pi over 8. That'd be at negative 3 pi over 8.
Baby.
And this point here at pi over 2.
Baby.
Minus
Baby.
3 pi over 2.
Baby.
Or 3 pi over 4. That'd be at negative pi over 4. So your point graph here would look something like this. It might help if you keep drawing the curve along the way so you don't get confused. Now I believe it, we said this point here was at negative pi over 4. So it'd be about right here. So that's what the graph would look like. This brown curve. If you're confused, you can ask me during class.